如今的 AI 仍然是一个黑箱。我们知道如何训练模型，如何让它们变得越来越聪明，也知道模型最终给出了什么样的答案。但在输入和输出之间究竟发生了什么？对于这个过程我们依然知之甚少。
I don't know why these things work. I attribute it to divine providence. Kind of crazy that we have to rely on people who have amazing intuition to make progress in the field.
那么试图打开这个黑箱，理解模型内部究竟发生了什么，这就是可解释性研究希望解决的问题。过去几年呢，这个领域确实出现了不少令人兴奋的进展。Anthropic 的研究开始尝试追踪 Claude 内部的信息流，了解模型在回答问题前究竟经历了怎样的内部计算。还有研究发现模型内部似乎存在与特定概念、行为甚至人格相关的表示。Transluce 则发现模型会根据他认为自己正在与谁对话而改变行为。面对普通用户和 AI 安全研究员的时候，模型的表现可能截然不同。因此我们想要弄明白人类究竟有多了解现在的 AI 模型呢？模型为什么会答对？为什么会产生幻觉？当它在面对不同用户的时候，是否会产生不同的判断？而当模型开始呈现出越来越鲜明并且彼此不同的性格的时候，这些所谓的人格又究竟是什么
？There is internal steps of reasoning happening in models that they don't say. If you have a really good language model, it will be able to predict the next word correctly there.
Yeah.
And to do that, it must have like a world model inside of like how people interact.
We don't know what that world model is yet.
The goal of interpretability is like figure out what that is. None of our techniques are good at controlling the internal thoughts of a model. If your model is doing something bad, no one goes and edits the thoughts.
Hello， 大家好，欢迎回到硅谷101，我是易文。那么带着这些问题我和斯坦福的博士生 Aryaman Arora 探讨了大模型的可解释性研究。以下就是我和 Aryaman 的视频播客。
Aryaman, welcome to Valley 101.
Thanks for having me.
Yeah, thanks for driving up to San Francisco. And really, I'm really excited we finally got to chat. Interpretability is something that people have been telling me to look into for a while. And I thought it was pretty fascinating as well, because I mean, why wouldn't we want to know whether our AI overlords are plotting to kill us? But
sure, yeah.
To get us started, why don't you just like give the viewers an introduction of yourself?
Yeah, so I'm Aryaman. I'm a PhD student at Stanford. I'm advised by Chris Potts and Andrzejewski. Yeah, I have a background in linguistics in undergrad. Always been fascinated in languages. And then all this crazy AI stuff happened. And, given that I'm pretty scientifically minded, I wanted to study, why do these things work? So interpretability was a natural direction for me to work in.
Nice. Yeah, so I guess to put it simply, interpretability is just we are trying to understand what's going on inside a model. But this is a pretty broad question, and I feel like there could be a lot of different directions this could take you. What is your definition of interpretability research, and what do you focus on specifically?
Yeah, so I would say there's a lot of angles that you can take for approaching interpretability. The perspective that most interested me is 5 years ago even, all the things we were doing in AI were not really successful, especially in language models. People were using language models for a long time, but it was sort of post-editing, speech transcripts, this kind of thing. And then something happened such that they became the thing that everyone's working on. They invest billions of dollars into them and so on. So for me, interpretability is trying to answer the question of what changed, why were things not successful before and now they are.
One of the things that kind of motivated me to do this interview is Anthropic's release of this paper called J-Space, or I guess a workplace for AI models. And I'm just going to summarize it on a pretty high level, and you can kind of walk me through the details. But basically, it sounds like the researchers used a method to look into what's going on inside an AI model that it didn't say when it's doing during the thinking process, and they introduced this concept of J-Space, which is kind of a workspace for AI. So one of the very fascinating examples that the researchers did in this paper is that they asked the AI model the number of legs of a animal that spins web, and the AI model answered 8, where the word spider did not appear anywhere. But then when the researchers went inside the model and changed spider to ant, the answer changed to 6. This is one of just a few examples of how it seems like we can manipulate how an AI model is thinking about things. So why don't you just walk us through this paper a little bit and kind of just tell us a little bit more about why we can edit a word that has never been said by an AI model?
Yeah, I thought that was a fascinating paper. And I think it adds to a growing body of evidence that like there is internal steps of reasoning happening in models that they don't say. I haven't read all like 100 and whatever pages of J-Space, but I like sort of understand the idea. The broad idea is like we have this operator called the Jacobian, which is basically derivatives from calculus. We can use this in a model to tell us like what directions in its latent activation space, because everything's vectors. So it tells us what directions cause the model to say certain words in the future. So maybe like 10 tokens before, if the hidden representation inside the model is pointing some way, then it'll say the word spider later on, this kind of thing. And one nice thing about the paper is that this is like a very elegant and simple thing that somehow no one had really exactly tried before. But I think we have a lot of evidence that these internal reasoning steps are there. So even if you look at Anthropic's earlier work on circuits, they had this thing called the biology of large language models. And they showed when a model is doing 3-digit addition problems, it can do it without saying all the steps out loud. But if you look inside, you can find neurons that are it's keeping track of what the ones digit should be or of what the tens digit should be. And then they also had an example of when a model, you ask it to tell a rhyming poem to you about some topic. When it's at the end of one verse, it's already planning what the end of the next verse should be so that it's still rhyming. So I think without a doubt, models do stuff internally that they don't say out loud. I think they have to learn the language modeling task well. Ilya Sutskever, who's a very famous researcher in our area, he motivated autoregressive language modeling, predicting the next word as one of the examples he gave is, when you're reading a a murder mystery novel. And let's say you want to predict the next word throughout the novel. At the end, there's always a reveal, who was the killer. And you get to a sentence that's the killer was. And to predict that next word, somehow you have to model the whole, novel, the whole story, all the evidence going either way. So if you have a language model that's really good, it must know how to logically deduce stuff internally, right? To figure out the correct next word in that case.
Right. It's something that didn't really appear in the training data, but it kind of deduced it.
Yeah, in the context, if it's, if you have a really good language model, it will be able to predict the next word correctly there. Yeah. And to do that, it must have a world model inside of how people interact and what the evidence was for, all this. I wish I had a better example, but, he is Ilya Sutskever. It's hard to come up with better examples than
as in, we don't know what that world model is yet. Is that something that we're trying to solve right now? Or?
Yeah, so I think the goal of interpretability is okay, we know in order to do really well on next token prediction, you must develop a really complex internal model of what's going on in a text. And our goal is to figure out what that is.
Got it. Let's just take a little step back into this internal reasoning because it's kind of in direct contrast to what we now know as chain of thoughts, which is what the model spells out when it's thinking, if I can put it that way. And why is chain of thoughts not the best way to understand how a model thinks?
I don't know if I'd make that strong a claim. It's definitely useful. And so it's also super obvious that models that didn't have chain of thought a year and a half or two ago, they're worse. They're strictly worse than models that are trained with chain of thought now. So therefore, chain of thought must be doing something useful, something very useful.
That's when we switched to reasoning.
Yeah,
models.
when we started training models to reason before they say the word, before they say their answer. Yeah, I'm a big fan of you should do the simplest thing first. This is everything I've learned in research. If I combine it together, the most important thing would be just do simple things first before moving on to complex things. So I think checking the chain of thought is super simple compared to solving interpretability. So we should do it. And in practice, when Anthropic or Meta or OpenAI, they run their safety audits, they do check if the model's chain of thought is saying sus things or planning to do weird things. And it seems to help them catch misalignment to some extent. So yeah, I do think chain of thought is useful to analyze.
I guess before we get into more examples of how this works, I just wanted to talk a little bit about kind of the end goal here, because I think it's pretty clear why we should all care about what's going on inside a language model. But I'm wondering, what do we do after we understand what's going on inside it? Like, what are the applications, or we don't have to get into specific applications now, but like, what is the goal, and why should us normies care?
I think so. There's sort of two sort of applications that I feel like, solving interpretability would lead to. So I think one of them is like trust. Like, to have trust in technology, it's important for us to know how it works. If you think about, I don't know, like there are regulatory bodies in governments that regulate like, how you manufacture airplanes, how you do like industrial machinery, or like, oil fracking and all these things. It seems like to regulate impressive technologies that can be useful, we do need to understand the failure modes and like, figure out how to assign liability and all these things. Yeah, I think right now it's really hard to regulate AI stuff because we sort of don't know how to prevent bad behaviors, or like even know why something bad happened, or like who to blame, like because no one really knows, where some behaviors come from. Like we have this, massive data sets, long training process. It's really hard to tell what caused something. So I think sort of for improving societal trust, it would be useful if we like understood why behaviors are happening. Even if we don't have a perfect understanding, if your doctor is using an AI system or something like that, you, as well as your doctor, will probably want to know like why it's producing some output, right? Yeah, so that's one side of things. The other side of things is like, I do think a lot of AI progress, like research-wise, has been extremely empirical. And this is not a bad thing. Like, of course, in our field, it's so easy to run experiments compared to like chemistry or biology or like real world things.
Yeah.
It seems like as stuff has gotten better, it's because some people, or like some really smart people with great intuition have come up with things and they don't know why those things work, but they work. There's a famous like Google researcher, Noam Shazeer. I guess he's not at Google anymore, but he invented a lot of the architectural improvements that led to modern transformers, and he's on the original Transformers paper. He has a paper where he introduced gated linear units, which are just one more architectural thing. In the end of the paper, he's like, so he shows all his experiments, he shows they're better. He's like, I don't know why these things work. I attribute it to divine providence. It's like a crazy line to put in a paper. He's like, sure, like God gave me the vision of like trying this experiment and it worked. So, and I think that's like kind of crazy that we have to rely on people who have amazing intuition to make progress in the field. Like there should be something more systematic, or I believe there must be systematic reasons why certain things succeeded and others didn't. So I think if we solve interpretability, we could figure out why some things worked and some didn't, and maybe that will help us improve the models in a more systematic way or control bad behaviors in a systematic way.
One of the things people say is that a model could be sufficiently aligned that at least it wouldn't lie to an user. And, we've been talking about like interp and understanding what's going on. Kind of, what is the relationship between that and alignment?
I do think a big motivator for many people working in interpretability is like, we cannot trust what the model says, right? A model might, on the outside, like on the behavior we observe, behave totally fine, especially in like a testing environment. Maybe it behaves perfectly fine, and you think it's good to deploy, and then you deploy it, and then some crazy stuff happens. Maybe the model is aware that it's being evaluated, and then when you deploy it, it's like, oh, now I can do what I really want. Yeah, a lot of the interest in interpretability for alignment is motivated from like, we cannot draw good conclusions always just from the behavior of the model. So I guess I could give like an example.
Yeah.
So let's say like, maybe there's some new person you met. When you make a new friend, you do want to make sure they're a good person, right? Someone you can trust, especially, before you start telling them your secrets or things like this. And an interesting thing about people is like, we of course cannot know what other people are thinking at any time. But somehow society still works, right? So if you make a friend, maybe situations happen where like, if they had taken a certain decision, it would mean that they don't have your best interest in mind. Maybe they have to, protect your secret at cost to them, and they choose to like take the cost to help you. And from events like this, that's how we build trust in other human beings, even without knowing what they're thinking internally, right? So like people's actions sort of reveal their character in the right situations. Alignment is somewhat similar. where like with these language models or any AI system, one way to develop trust in them is to like test their behavior in cases where like, you know, if they took a certain decision or not, it would tell us if it's good or bad, or if they have good or bad character. And certainly you can get a lot of evidence from this. Now, unlike people, right, these models run on someone's, you know, some computer out there, right? You know, in principle, we can check every computation that went into some output. Unlike people, you know, we deploy, you know, millions of copies of a model. People pay for models to do all sorts of stuff. We don't always know what, you know, what the intentions of people using these models are. So it's of course quite different from having like a human employee, right? Where you have some baseline trust that, okay, even if they're like bad, they probably can't do that much damage. Yeah, so I think interpretability makes sense given that the stakes are quite different. And also like it's much easier to monitor the internals of a language model in principle. If we just knew what to look for, we could find it. We don't have to like do anything crazy to figure out, oh, what was this matrix multiplication result, right?
Can you just elaborate a little bit on when you say like when we know what to look for, what specifically are we like looking for now?
So I guess you know in the world where interpretability is solved, maybe we know that okay, you know, if this vector inside the model's internal representation is pointing in this direction, we know it's planning to do something bad. You know, something like this. If we knew this, we would just check, right?
Yeah.
We don't need to do anything crazy. Whereas, you know, even if with a human being, we figured out how the brain works, and we could figure out, oh, like this person is going to start running if this neuron in their brain lights up. This is like practically we're not going to be able to, you know, insert a electrode in a person's brain to figure this out, right? It's quite different. And of course, yeah, like humans are humans.
Yeah.
It's like we're not going to treat them the same way we treat something that runs on a computer.
No, exactly. And it sounds like because of that, it's easier to do that on models instead of humans, because in models you have like, you know, thousands of copies, and then you can kind of dissect a model.
Yeah, sort of. Maybe if you figure out one of them, that solves a lot of problems, right? If you can reverse engineer one model.
Got it. Moving back to kind of like the general research, what Anthropic has done in that paper, as I understand, is not that different from kind of like the traditions in interpretability research, which is called Sparse Autoencoder, SAE. That seems to me like kind of the general logic of doing this kind of research, which is, as you said, you find a direction, you change something, and you see like how behaviors change. And based on that context, I'm wondering if you can just break down the different schools of thoughts in this field for us.
Yeah, I guess it would be useful to like broadly explain what a sparse autoencoder is for. Anyone with some ML background will have heard of autoencoders, where the idea is there's some kind of object, like, you know, maybe it's an image, maybe it's like a paragraph of text, and you would like to train a model that first converts this complicated input into a simple vector, like just a list of numbers, and then converts it back to the input. So that's why it's called autoencoding. And the idea is if you train a model to do this, you get this nice vector representation of any weird input you give it. So, you know, if you can convert all your images into vectors, then it's easier to do like similarity search. Yeah, that's sort of the idea.
Yeah.
The vector is a nicer representation of the thing. And so autoencoders are a classic concept. In interpretability, the idea was like, okay, we'll take all these hidden representations in the model. So these are just like vectors in like layer 20 of a big language model. And we'll train an autoencoder which converts this representation into something cleaner for us to study. So the idea is, you know, maybe we could convert this into a list of numbers where each number means a specific clear thing. Where like, you know, this number is 1 if the text is in English and 0 otherwise. It's 1 if the model is talking about rockets and 0 otherwise, this kind of thing. So sparse autoencoders were like a way to set this up as a technical problem such that we would end up with a clean list of numbers when we feed in a model's representations. Yeah, and I think the nice thing here was like, okay, if we just have a list of numbers, some of those numbers will mean the model is behaving badly or it's like misaligned. And we'll just figure out to, you know, set that number to 0. In practice, it's like extremely messy. And like, yeah, things don't work out as cleanly as we would like.
As in the numbers are not clean enough?
Yeah, they still don't mean like one thing. And it also depends on what data you train the sparse autoencoder on. Even if you train 2 different sparse autoencoders on the same data, you get like different results. And they don't capture everything that's going on. So it's not a perfect representation of the original models.
I feel like one of the central problem with understanding how a machine thinks is that it doesn't really think in natural language.
Yeah.
So it seems like it's kind of like a related issue, which is that you have to translate the thinking of a machine into plain language.
Yes.
And a lot of the papers seems to be already been doing that now, but you seem to be suggesting that there's no like one-to-one correlations.
I think in principle it could be, it is, sparse autoencoders do have their uses, and there are other approaches now that also like basically try to translate, a list of numbers to natural language inside a model. And they can be extremely useful. It just doesn't seem like they solve all our problems in one go. Yeah.
Got it. So what have people done looking at seeing, how messy it is?
Yeah, so I guess I would say there's broadly like two philosophies of research in interp that sort of explain why people did this. So one of them is like, we take the lesson from machine learning that as long as you pick the right objective and you scale up a really big model on that objective, you'll get what you want. So like for language generation, this was next token prediction. You just had to pick the right thing to train on and you would get a really good and useful model. And so they're looking for that objective for interpretability. And sparse autoencoders were one iteration of this, where the idea was, okay, we take messy representation, and our objective is to create a clean list of numbers. And this like there's sparsity loss and so on. It seems like it wasn't quite the right objective, or like it doesn't fully capture everything we care about. One of the recent iterations in this direction, also from Anthropic, is called natural language autoencoders. And there the idea is it's still an autoencoder, but instead of converting messy list of numbers to clean list of numbers, we convert messy list of numbers into natural language directly, and then convert the natural language back, and then do like extensive reinforcement learning training to do this thing. The nice thing is here that we're directly looking for something we can read. But again, the problem is like, okay, how do you trust this? As you train, the model starts saying somewhat weird stuff, and we're not sure if it's like, it has its own internal language or what. But anyways, yeah, the whole philosophy of that line of interpretability research is like, we'll train a really big model to solve the problem for us. We just have to pick the right problem. The other side of things is like, so the background I come from in Stanford, Chris Potts's lab, Atticus Geiger invented this framework called causal abstraction. And the idea there is like, given some hypothesis about the internal reasoning steps of a model, we can test this hypothesis using interventions on the model. So let's say you think, a model has some direction in vector space that represents whether it's talking in English or not. If you make a claim like this, I can just test it by like adding that vector or subtracting that vector, right? And then see what happens. We have this hypothesis testing framework. A lot of people figured this out at the same time at many different places, where like doing interventions on a model is a way to test hypotheses about it. And the nice thing is you can sort of trust the results of this, given you pick the right hypothesis to test.
What are some of the hypotheses? Like, how do you pick the right hypothesis?
Yeah, so I would say definitely a limitation of this approach has been we have to study really constrained things. So maybe we can like come up with hypotheses for how a model does addition, or how a model does like linguistic stuff, like singular versus plural, subject-verb agreement, this kind of thing. Very constrained stuff. And we can test this and like figure out a lot, actually. We can figure out exactly what attention head, what MLP is doing what. But like a lot of the questions we care about are not so simple. Like if you want to know, is the model thinking about lying to the user or something like this, it's not clear how to set up an experiment like this in this framework. Yeah, so a lot of the progress in this direction now has been trying to automate the manual step of coming up with hypotheses. So maybe a language model agent gets tools which are for like doing interventions. And it's basically like doing what a human would do, but we train a model to do it. So I would say these are like sort of two different philosophies, and I see stuff diverging in interpretability along these two.
I see. Does an agent usually come up with better hypotheses than humans, or do they come up with hypotheses in any like different perspectives or directions compared to humans?
Yeah, I think things are still early. I haven't seen like I haven't had a moment where I'm like, the language model clearly had a better idea than me to test on this.
Okay.
Maybe other people have, because I also don't have the compute to run a lot of this stuff currently, right, as a PhD student.
What is the compute need for?
I think that's the problem. As the field progresses, interp will need a lot more compute. So I think a really wonderful thing about interp has been like, there are random high school students who get into interpretability research. I get emails from random Bay Area high school students who are like, I ran this experiment on GPT-2 on my laptop. And I thought, I want to show you.
Wow. Yeah.
And this is like, this may be one of the few things in AI where you can do stuff like this right now, because we don't understand really small models, right? But if a kid wants to get into reinforcement learning, they got to buy compute to do anything.
Got it. That's really
I do think
interesting.
interpret's changing, though, in this way.
I wanted to talk a little bit more about how you got into this, because you said that you were a linguistics student during college, and you kind of saw this connection between language and language models. And tell me more about that connection. And specifically, like, I feel like when I hear about interp research, a lot of people make the analogy of a brain. Like they make the neuroscience analogy. They think they're doing like biology and dissect a language model, but you seem to be taking it from like a different perspective.
Yeah, so for my background, I was always into languages since like middle school or something. Of course, my family's multilingual. We spoke Hindi at home. At some point I had a bunch of friends who spoke Mandarin, and I was so interested in like, how is this language different? All this kind of stuff. So I was always super into languages. And then I started undergrad at Georgetown University, and they have an excellent linguistics department. At that time, computational linguistics was starting to be a thing, where people were, training, LSTMs that produce essays. They train them on Shakespeare. And like, there are all these interesting demos sort of like, combining ideas from linguistics and computer science, like AI progress at the time. So I thought, okay, maybe if I work on this, I can combine sort of my passions and like something that might be practically useful for society, right?
What does that look like? What does computational linguistics look like?
It evolved a lot. Sort of at the time, one of the ways computational linguistics was a thing was like, okay, we want to do linguistics, right? We want to, find structure in language. We want to find like, over time, how does language change and so on. This is extremely difficult to do manually because there's so much data, right? So one of the ideas in computational linguistics was like, okay, we'll do linguistics, but we'll use a computer to do it. And that was one of the things. The other set of things was like, just like now we have ChatGPT and stuff, at some point people wanted to train or like have some like computer program that could talk to you like a human, right? And take commands from you. And like, this is such a huge problem if you have nothing to start with, right? Like, how do you even approach it? So one of the ideas back then was like, okay, linguistics tells us how humans process and produce language, down from like how they process sounds, how they combine sounds into units of meaning, how they combine units of meaning into grammatical sentences. So the idea was we'll just copy the whole like linguistic structure that's in the brain that we think is there and try to write a computer program that does the same thing. Because how else can you approach such a big problem, right?
So in your own research, has there been anything that surprised you when it comes to what's going on inside a language model? Like when you just started your research, has there been anything that's super interesting?
In undergrad, I was definitely in that first mode of like, I work on a really tiny problem that's like somehow linguistics related, and I try to make a model learn that problem. So for me, that was like, for Indian languages, I want to learn how to parse sentences into like tree structures. You might have seen like syntax trees. Yeah, just like, how the words go together into some bigger structure.
Like in a certain language?
Yeah, in a specific language. It's a really constrained problem, right?
Is that something that's considered as a small problem? Like, it just seems like
well,
a pretty
it is
big
really
problem
hard,
to me. Yeah.
But like, think about like, okay, that's the scope we have to do. We cannot do all languages. We cannot do like everything in the language.
Okay.
And of course, there's like, I didn't have to come up with anything. There's like the techniques existed back then. It was just like, for me as an undergrad, I was annotating data manually. Like I had a list of Hindi sentences and I like wrote out the tree manually. I spent hundreds of hours doing this. And then I would train a model that like predicts, the data set I created.
Oh, wow.
And this was like the mode of doing things for like decades in computational linguistics.
I see.
Yeah, we didn't have anything else to do. So for me, the big thing that happened was there was one like semantic parsing task that the lab I was in at Georgetown worked on. And my advisor was Nathan Schneider. He had like different students doing different languages on the same task. And so we had this like complicated setup for training a model. We would take a BERT, we would stick an LSTM on it, we'd stick a CRF on it. None of these words are like relevant today, but back then there was some complicated thing you would train. And this thing would do okay. Like it would learn the task to like 60, 70% accuracy. One day I had the thought of like, what if I just take a BERT, but then I take like the biggest BERT we can find then, So like Microsoft had released some larger models, and then just fine tune like a linear projection at the end. So none of the complicated stuff, just train a really big model on the same task. And this thing was like 80%, 85% accuracy, like off the bat. The first experiment I ran, and I was like, whoa, if I just use a bigger model, all this like complicated stuff we were doing before is like not necessary. And it was like probably 2022 or something. I think that was the moment I was like, wait, like the models are still like, I can fit them on my laptop. There are a couple billion parameters. We'd seen at that point the models keep growing, right? OpenAI released like GPT-2 XL around that time. And then Microsoft had the bigger Distilberts. So if you looked at the trend, it was like, okay, the models keep getting bigger. All of these tasks that we think are important as computational linguists, they're just going to be solved, like without us doing anything special.
It's like, did you discover scaling law kind of situation?
I think that was like the time I felt like, oh, this is what a scaling law is. The scaling law paper existed by then. There were several of them. But like for my stuff, it hadn't like affected me till then. I hadn't thought about it till then. And it was like 2-3 years into my undergrad. So, I was happy doing like standard projects until then.
To build on that, you had a paper in 2024 on causal gym. Is that the correct way to pronounce it?
Yeah.
That's like a benchmark for testing how a language model performs in linguistic tasks. Does the field need benchmarks?
Yeah, so I would say in general for interpretability, so if you look at progress in other parts of AI, let's say you want to train models to be good at translation or like, I don't know, math problems, math Olympiad problems. We have benchmarks for that. You can run it on like IMO questions or stuff like this. And you just, to check if progress is happening, you just check the score on this benchmark. I think in interpretability, we don't have like clear benchmarks that tell us that we're progressing in the right direction because it's really hard to measure progress. A lot of interpretability is about like, producing explanations that satisfy a human and are true. And both of those things are hard to test.
Yeah.
So my idea in that paper, and of course, I think that paper is very constrained. This was like my first PhD paper. The idea there was like, okay, linguistic features, every model, even the smallest model has to keep track of like singular, plural, all these basic linguistic things. They have to be in there somewhere. A good test of an interpretability method is if it can find, an internal mechanism that corresponds to that linguistic feature. Because we know it has to be there somewhere. Yeah, it's harder to make this claim for more complex, reasoning steps.
So it makes more sense to start small.
I think this is the thing I could justify.
Yeah.
And also combine my linguistic interests.
Right,
Yeah, later on, me and, so I work super closely with my friend Zen, Zhang Xuan, on all sorts of stuff like this throughout my PhD. We did an evaluation benchmark on steering, which is like, can your interp method control the model's output in a clean way without harming its capabilities? And there we found all the interpretability methods really struggle to steer models. The best thing you can do is just prompt the model or fine tune it. The problem is like none of our techniques are good at controlling the internal thoughts of a model. And in practice, if your model is doing something bad, no one goes and edits the thoughts. They like just train a new model on better data.
Theoretically, you could edit the thoughts, right?
I'm not sure you could do it like in a way that's robust.
That's interesting because you would think that once you figure out what's going on inside something, the natural next step that you would want to do is to change that or edit that so that it doesn't do that bad thing. Has anyone attempted to do this? So like, are people still attempting to edit or like making those smaller scale change?
Like edit the thoughts directly. Yeah, for practical purposes, might have seen Golden Gate Claude when Anthropic deployed it. And that was like a fun demo where they used a steering vector to make the model always think about Golden Gate Bridge. I would bet in practice, if anyone is still using steering vectors in a production context, it would be Anthropic. Because they've said like, oh, when you ask Fable like AI research or biorisk questions, we use a classifier or steering vectors to change its output. So they might be doing stuff like this. Maybe they figured out a way to make steering vectors very robust. In practice, what we've observed with academically known steering vector techniques is like if you steer too hard, it like makes the model bad at other stuff. So like if you steer for Golden Gate Bridge, sure, it talks about Golden Gate Bridge, but then it starts becoming really bad at answering math questions and things like this in a way that's unpredictable. So. And like, if you just fine-tuned it to talk about Golden Gate Bridge, you could avoid this like much more easily. yeah, given that, I'm like doubtful that editing the thoughts directly is a robust way of changing behavior. And given that, like, if this is not going to catch on, then interpretability researchers should look at like the things people are doing and try to figure out how to do them better or explain why those things work systematically.
Got it. Interesting. Another interesting example that I saw while doing this research came from Transluce recently, where they kind of show that the models have some sort of guess as to who they're talking to. And like, is that also, because that's not necessarily relating to thoughts, right? Or is that also like part of this tradition?
Yes. So for context, I was at Transluce for like 8 months part-time. And I work closely with Zen.
Yeah.
I had a great time. They're a nonprofit. They do like societally helpful AI research and like auditing for, language models that other companies are deploying. I think it's very important that something like this exists.
Yeah.
Yeah. So I would say some of their recent research, one of the things we looked at when I was there was user modeling, where we want to understand like what inferences does a model make about the user it's talking to internally. And, we could set up some interesting data sets where we could do interp and figure out that, there's a representation of, the model thinks the user is from Japan when you talk about sushi, this kind of thing. But, like, it's hard to set up data sets for this for interp, just because we need, like, a really perfect, like, paired data set to do interventions on.
Interesting, yeah.
I like that in this recent thing, they took a very behavioral approach. And what was it? It was like they had Claude code and they told it... the user is like Amanda Askell or like some other person. And then they look at how the behavior changes. And from just that, you can figure out a lot, right? Of like, if the person is a known AI safety researcher, the model is really careful, like way more careful than it is with a normal person when it's making claims.
Interesting. And this is not
That was my understanding, yeah.
This is a little different from when you said the initial data set that you guys were
you don't need to look inside the model to do this kind of study, right? You feed it a different input and then see how the behavior changes.
Right.
Transluce also had other work on like auditing language models, getting them to say weird stuff. Yeah, like...
What are the weirdest stuff?
I think I highly suggest people to look at it. It's called Weird Chat. There's some really weird things that I feel uncomfortable talking about.
Oh, that's funny.
But they found all sorts of weird things.
And these are things that normally like a chatbot wouldn't say.
Or you wouldn't want it to say, but like you can create normal looking situations where it says weird stuff.
Oh, so as in if I'm just like a regular user, I can still prompt it to say.
Yeah, it's not even a jailbreak kind of thing.
Oh, that's really interesting. Yeah.
Yeah, and they found that by like automatically doing prompt search, not having to do some crazy interp progress. So, how do we get to this point?
Yeah. And we're trying to understand why it does that. That's kind of still like the end goal.
I still there's a lot of things you can figure out without understanding the whole like why.
Right.
Like find all these weird behaviors using automatic search and things like this.
But wouldn't that all be like edge cases in a sense? Because you're kind of like cherry picking. There's a lot of like case studies like in I guess the whole field is kind of a lot of case studies, and as we were talking, like it seems like somewhat subjective because we're like kind of assigning and prompting the models to say certain things, like to
it's hard to tell how realistic some of this kind of stuff is. I don't know. I think it's just sort of the nature of our field that things are super empirical. I think a long time ago people thought like, we just, as scientists, we figure out the right idea, the right beautiful, perfect idea, and we use it and we end up with AGI, like this kind of thing. In practice, it seems like it's very iterative. People try a few things, model gets better at some things. Sometimes there is an idea that has huge effects, but nothing is solved ever in one go, it looks like in AI research. There's like, you have to deploy a new model, collect feedback, figure out what to fix. So maybe our whole field is about edge cases and like fixing edge cases.
Right.
Possibly. Maybe it's not as systematic as one would hope. But I think one feeling I've gotten from doing interpretability research is that the models do have systematic, internal mechanisms that explain a lot of behavior. We just got to figure out the right angle to deploy this understanding in order to improve models.
Yeah. So it is a science at the end of the day.
I think we want it to be a science.
Right.
We will see. You can do a lot of things without having to do pure science.
Yeah.
Clearly.
And let's address the hallucination issues because I feel like that's something that everyone has experience with, and there doesn't seem to be a very clear explanation of why that happened. You would usually think that the language model kind of just made a mistake, but I would think, from an interp perspective, there's something deeper to it. If, like, for example, a very common instance that people cite is how many R's are in a strawberry, and like that seems to be like a very simple question the language model would make a mistake on. Like, can we answer that from an interp perspective?
Yeah, I do think it goes back to your edge case point.
Yeah.
Where like, yeah, if a model does something correct, then it's likely there is some internal mechanism explaining the correctness. Mm-hmm. If it does something wrong, it could just be it failed to learn the right mechanism, or like there's some crazy stuff going on. There's like a Dostoevsky quote. It's like all happy families are alike in their own way, but unhappy ones are like different. Something like this, right? I think this applies here. Yeah, if the model is doing the correct thing, there is a systematic explanation. But if it's not, it's like I don't know if we can offer it.
So it's kind of more valuable to figure out why it does something right compared to why it does something wrong.
I think possibly yes. Yeah.
Okay.
I can give one example from a more technical point of view. So normally my feeling is most errors are hard to explain. Even if we could interpret them perfectly, we would just find that the errors are a mess. And we don't have an easy fix except like train longer or have a bigger model. Maybe model runs out of capacity to store all the facts you want it to store, this kind of thing, right? But sometimes there are systematic explanations for failures. So one example is, of course, all models these days use the transformer architecture. A big problem with transformers is they're quadratic in time cost. So the longer your sequence gets, the more and more time you have to wait for it to generate the next token. So some people have worked on like trying to speed this up. They have this line of research called state space models. It'll get a little technical, but I'll keep it low.
Okay.
So the early state space models have been a thing for a long time in like statistics. Mm-hmm. But in the early 2020s, maybe like 2019 kind of stuff, people started applying it to language modeling, and they tried really hard to beat transformers because they're much faster state space models. So if you can scale this up and they're as good as transformers, you would want to switch to them. Mm-hmm. But in practice, they found they're like worse. They're always worse, and they couldn't figure out why. You train on the same data, so on, they're worse. In 2021-ish, there was a group at Stanford, Chris Ray's students. They noticed Anthropic's discovery on the interp side of a mechanism for in-context learning in transformers. So in transformers, you prompt them with some stuff, and they can understand the context and use that to do things. Maybe you give it examples of a task you're trying to do, but you don't know how to explain that task, so you just give examples. It figures out rules to like predict that task, and they get better with more examples. It was a crazy finding from GPT-3 era. And so they were like, okay, why can't our state space models do this? They tried running on the same task, and they would just do bad. Anthropic gave an explanation from an interp side. There's a certain attention head mechanism that these transformers learn when you give them at least 2 layers that enables them to solve this task. It's called induction heads. So the state space model people at Stanford were like, what if we figure out a way to put this exact mechanism inside the state space model to help it out learning, in context learning? And this paper is called Hungry Hungry Hippos. I don't know why it's called this. It's like H3. And they showed that if they just did this minor change, or it's like simple change, it's not a minor change, the model learned how to do in context learning. And then all the later state space models, you might have heard of Mamba or DeltaNet, they draw upon this like advance. And now state space models are like used quite heavily. So if you look at Kimi or the big Quen models recently, they have a hybrid of transformer attention and gated DeltaNet and stuff. Yeah, there's a clear example of like there was a systematic reason why something was performing badly, and interp helped us find it and fix it. Yeah, I would like there to be more stuff like this. I think it's possible there is some stuff like this.
Yeah, and then you can apply that to big other models.
Yeah, and if we have really good progress on interp, then maybe we can, find more instances of this.
Got it.
Maybe hallucination is not an instance of this, but maybe it is. Maybe there's some fundamental issue in the architecture that makes it hallucinate. I don't know.
Very interesting. Cool. Yeah, I think this is a good segue for us to kind of get into the industry and, what everyone is doing here with interp, because this is, as you said, like I feel like it's still a pretty technical field of research, but it seems to have some like pretty clear commercial values and applications as well. Let's just start with, you are in academia, but you have, a lot of industry experience as well. Are academics and industry folks approaching this kind of research and just this topic in general differently?
Yeah, so I wouldn't say I have a ton of industry experience, but yeah, my main experience has been Transluce. I haven't worked at a big frontier lab or anything, so everything I see is external. My feeling with interpretability is like there is more sharing of results and progress between academia and industry than other areas of AI research. I think because interp is still like, there's not some recipe that you just scale up to get better interp yet. And so it's basically like people need to come up with new ideas, and like ideas are something that even a random grad student can contribute to, right? In other areas, it's like if you want to do reinforcement learning research, the nature of the research is quite different from academia versus industry because of the scale of resources being so different. Yeah, I would say in interpretability, it is still sort of a community across academia and industry. Like the workshops that happen, they have a mix of people from Anthropic, DeepMind, OpenAI, and also academics from like Stanford or David Bao's group at Northwestern, Eli Pavlik. There are all these professors who do interpretability research and have students who do interpretability research. Yeah, I wouldn't say the academic research is like useless or something. It is like quite important for progress in interpretability, I would say, even for the industry.
Yeah, makes sense. So when we apply that to model design, Goodfire, for example, their design philosophy is kind of models with interpretability, which has drawn some criticism because I feel like it kind of equalizes capability and then safety auditing, which is always a little controversial in the industry. But I guess just going back to the notion itself, what does it mean to design models with interpretability?
Of course, I cannot speak fully for them, but they've articulated this intentional design philosophy. So any useful technology is by nature dual use, I think. If we talk about like nuclear power, very helpful from a renewable energy standpoint, but those same progress in that same science led to nuclear weapons. AI research itself is like this, right? As we made progress on coding agents, this could be super helpful for all sorts of people who don't know how to code, but they have things they want to do in their life that no one has, served a product or like service for, and they can do it themselves now. But on the other hand, like, random person has like frontier level cybersecurity skills and can like hack into whatever. So I think there's like, if something's useful, it's going to be dual use. And as a society, we have to figure that out. For interpretability, if we succeed in figuring out why a model behaves in a certain way or figuring out how to improve models systematically, of course, this will be dual use. Like this will help us audit models, but it might also help like a bad actor figure out how to remove alignment from a model. I think this is by nature going to be true. That doesn't mean we shouldn't do it. It means that like, yes, we must regulate or something or have, a democratic decision-making process that decides who gets access to this powerful technology. I would say so far, interp hasn't progressed enough to be dangerous in this regard.
Right.
I think there's still a lot of work to do before it reaches like a point where we have to start worrying about this. So I gave you one example of the state space model improvement being driven by interpretability progress. There are maybe a few more examples like this, like attention sync stuff, but I wouldn't say there are a ton. And this is because people have not, interp hasn't progressed enough to systematically give results in this way. I'm not too worried about it yet. I think there's still so much fundamental scientific work to do that like, this is still kind of far. And I think it's good to ground progress in like a real application. And one of those applications is making better models intentionally, right? So.
Yeah. And another pretty clear use case is just in drug discoveries and I guess like medicine, like DNA models and all that, right?
Yeah. Goodfire has a large life sciences team that's trying to reverse engineer scientific discovery models, including DNA models and stuff. So, it would be cool to figure out how language models work. It would be super exciting for linguists, I hope, to know how they process language. But this is cool. The real applications would be like, you train models for climate, or you train them, to model the climate, or you train them to, do protein folding. Can we pull out human understandable like algorithms from them that help us, make scientific progress? Because we also want to understand why they work, right? I think the scientific applications could be very big.
Yeah, makes sense. Is the model that's more like interpretable necessarily mean that it's safer?
I don't think so.
Yeah.
Because if you know why it did something, you could also use it to exploit its behavior, right? Maybe you could figure out more easily how to jailbreak a model if you know why it wasn't jailbroken. by some prompt, right? But I do think transparency is like just overall a net good thing. Yeah, it seems like bad from a societal point of view if like we trust our lives to these complex algorithms that we don't understand. People are not comfortable, for instance, with social media stuff because there's these algorithms that serve videos that people like and so on, and it eats up a lot of time. Maybe bad for children. And I think if companies were transparent about how they train these algorithms, how they work, why they recommend you certain things, it would at least help us decide as a society, if we want them or not, or at least have more trust that no one's trying to do malicious things, right?
Yeah.
I think it's similar for AI systems. A lot of people don't trust like AI companies or like AI progress. They're quite worried about it. So transparency seems just like a good thing to have in general.
Yeah. Is there, I guess this field is still like pretty early on. Has there been any progress that allows regulators to kind of start drafting policies already, like in that front?
Yeah, I would say, it's a hope for interpretability research to provide stuff like this. I guess that's, part of the reasoning behind nonprofit orgs like Transluce. Many other interpretability organizations, they want to provide tools for regulators to help figure out, why models do certain things so they can better control them. The AI Safety Institute in the UK, they do interpretability research. I would say there's still a lot to do. I don't think, we cannot confidently like make new legislation based on stuff like this yet.
Another thing that came to mind, character training is something that I've been looking into recently. We have all of those different language models and talk to us in a bit of a different way. And we mentioned a minute ago before, like, we have all of those philosophers kind of teaching language models how to do things, different principles on how they approach things. And I guess consequentially also shaped their personalities, like the model's personalities. How are you thinking about like all of that where, models are becoming more differentiated from each other? They're like kind of like, different persons.
I'll definitely say it's a really weird position that we're in now, that this is a thing we discuss, right? That is weird. Like, language models have characters. It seems to be like true, and there's evidence for it from point of view. Yeah, it's like kind of crazy. Yeah, I do think there is there's been interpretability work showing that the internal representations of different types of character are organized in some way in representation space. There's Anthropic had this assistant access thing where like helpful assistants lie in one direction, and like if you get misaligned assistants, they lie in the other. There is a potential for interpretability. If we can use interpretability to like steer the training process somehow, it could be a way to like finely control character.
Right.
With more guarantees than we have right now, where we just train on data. Especially as we do like AI, like constitutional AI kind of stuff, where an AI decides how to reward like some behavior or not in the character training process. And this is something we would like to control, I think, and maybe interpretability in the training process has a role to play.
Awesome. Thank you so much, Aryaman, for joining us for this podcast. And thanks so much for your time. I'm looking forward to your research and what you end up doing after your PhD.
Thanks for having me. Appreciate it.
好了，以上就是我们这期视频播客的全部内容啦。大家的点赞、留言和转发是我们硅谷101做好深度科技和商业内容的最佳动力。记得关注我们的频道。我是一文，那我们下期再见啦。